2, 3 of us Indians, my husband, another friend, and us. So we are about the only people of the wrong color, and I used to feel I'm the wrong color and wrong sex. If you bring two of these Majorana quasi-particles together, they have two possibilities. They can either become an electron or they can completely disappear.
Say how far we are from a practical quantum computer now.
Yeah, that's the million-dollar question, so to speak. I know young women who find it difficult to get positions as faculty members once they're kind of labeled as difficult. Institutes don't want to hire, say that they cannot hire two people at the same time. Maybe you give them an extra position at that time.
As we celebrate International Women's Day this month, let's listen to the story of a world-renowned Indian women scientist who has defied the biases and carved her own path in the academia and emerged as a versatile scientist whose work spans elementary particle physics, condensed matter physics, and the topological quantum matter. Welcome to a new episode of the Science Talk with the versatile scientist Professor Sumathi Rao, whose contributions have shaped our understanding of quantum wires, quantum dots, and the fascinating world of anions and topological quantum computation, which is of great importance as Microsoft recently revealed Majorana 1 as the world's first quantum processor powered by topological qubits, which makes a transformative leap toward practical quantum computing. Also, the challenges of being a woman in Indian academia, especially the biases she faced for being the wife of a world famous scientist in the same field, and how she navigated these biases and became a versatile scientist. She is a fellow of the National Academy of Sciences, India, the Indian Academy of Sciences, and the American Physical Society. Professor Sumathi Rao, a warm welcome to the Science Talk. And we are deeply honored to have you in our studio so that our conversation to be in person.
Thank you so much for inviting me to this Science Talk. I'm actually deeply honored to be here. I'm very happy to be here.
So before we delve into your research, we would love to hear your story first. How the bright student from Gujarat emerged as this versatile scientist.
Actually, I was always interested in science, and as a young student growing up in Baroda in a school, and I read even as a school student, used to read about popular science, which my father also encouraged me to read popular science articles. And then at some point I had to make a choice between science and engineering. And fortunately for me, I got the National Science Talent Scholarship. So that kind of propelled me more towards science. And that used to, in those days, give scholarships. So with those, my parents encouraged me to buy books. And I remember getting lectures on physics by Feynman. And that was a very nice kind of introduction to, it was not exactly at a popular level, it was higher than my level at that time, but it was also very readable, very charmingly written. So I got interested in that. And so Richard Feynman has always been one of these heroes of mine. And that's how I started in my career.
Even though you got admission for engineering at IIT, you chose physics.
I chose
so
physics.
What inspired you to choose physics or
engineering? As I said, one of this thing at that time was a choice between engineering and science, and then getting this NSTS helped me decide that science was also, I mean, I wanted to do science, but I was also worried about the fact that most of the good students went into engineering, so that bias would be there. But this scholarship helped me, and in some sense I should assume that also being a woman at that time must have helped me, because most boys are pushed into science, physics, engineering even if they don't want to, because they think that that is better for their career. But as a young woman, at least I was allowed free to choose whatever subject I wanted.
Your family also supported?
My family supported. They would have said, my sister did engineering, younger sister. So there would not have been, there was not a bias against education in our family. So that way we were very lucky. that our parents always wanted us to succeed, my mom in particular.
Then how was at IIT Mumbai at that
Uh,
time?
I did my bachelor's actually. I did not go at that time to IIT because I was very homesick. So I decided to stay back and do my bachelor's in Baroda, MS University. So that's where I did my bachelor's. And then I moved to this
IIT.
IIT for my master's. So my bachelor's in in Baroda was very peaceful. I mean, I was still staying at home. And the teachers were encouraging. There was one particular professor, Bandukwala, who was very encouraging. So, and he would tell me about earlier students of his who have gone ahead and done good work. And then when I went to IIT, I was again very lucky. We had a class with about 8, half the class was girls. So even though within IIT there are a lot of biases against women, we were kind of immune from it because we were a big batch. We didn't care what the rest of the people did. There was enough of us to sustain our interest in physics.
So you faced no bias during your student days in
No,
India?
I would say that during my student days and even IIT days, we did not even realize that there were biases because we were kind of immune from all these things. Only when we started asking for recommendation letters to go abroad, we would hear things like, "Oh, you're a girl. Do you think you'll be able to do a PhD abroad? Do you think your parents would send you?" Those kinds of questions.
Also, there is a thinking that this physics and maths are for men only.
Yeah, but those biases we came to realize much later. I mean, later in career. At least till the master's level, I would say that I did not really think that there were biases.
When you went abroad for PhD?
When we went abroad again, what happened was there were very few Indians in our. I mean, there were 5 Indians out of many. And in my batch, out of those 5, 2 were girls. So I've been, in some sense, in this thing that I did not think that there were very few girls. But when we went abroad, we saw that mostly the few women in our class were of Asian descent and so on. The local women were very few, right? And slowly we realized about the amount of biases. Then people would say things and so on. So those things happen. But again, I would say I was lucky till I had a young professor as a PhD supervisor who did not discriminate against me. And I had a reasonably good time throughout my PhD. And when I went as a postdoc then to Fermilab, then I found that I was in the Midwest, there you suddenly find that you're the single woman among a large number of men. You're the youngest because there are only postdocs there are no students. And then there were 2, 3 of us Indians, my husband, another friend, and us. So we are about the only people of the wrong color. And I used to feel I'm the wrong color and wrong sex. So that was the time
so
when
you felt very lonely at the Fermilab there.
Yeah, at Fermilab.
Being the youngest and the
Being
women,
the only very few students, very few postdocs, and mostly faculty, and mostly Westerners, and very few Indians. So that was the time we started feeling a little that, okay, maybe you're different from the rest, right? Which again, my husband and the other Indian postdocs, the men, did not feel as, they were also of the wrong color, but they didn't seem to feel it as much.
We would like to know your love story also, that is how you met Professor Ashok Sen and what attracted
we were both actually students.
Because you belong to different cultures, languages, cuisines different.
We were different languages and he's Bengali, I'm Tamilian. And so it's very different culturally, this thing. But actually at that stage when you're young and a student abroad, you don't really think of these things. All of us are students together.
All of us are Indians.
All of us are Indian students. And there's so much more in common than these differences. Right? We spoke in English. Actually, Ashok was at that time, he's from a Bengali medium school. So he had a more accented English. I was from convent. We were in the same corridor. We used to, cook in the same, we started cooking together, eating together, even though our food habits are very different.
You are strictly
I'm
vegetarian.
strictly vegetarian.
He's
He's
non-vegetarian.
non-vegetarian.
So how you cook together? Same
No,
kitchen?
same kitchen, because we were used to the same kitchen even in our this thing. But I mean, Ashok likes cooking much more than I do, and so I mean, because he has to cook non-veg and I don't at all cook that. So mainly he likes taking over a lot of the cooking, and I'm not as fussy about food. Whereas Bengalis love food, like they're like Kerala people in that way. I
Okay.
think Bengalis and Kerala people have a lot in common.
And after returning to India, you and
Yeah.
Professor Sen lived in separate cities
Yeah.
for almost a decade.
Because even in
What was the
Fermilab we were
reason?
together as postdocs, but after that he went to Stanford and I went to Madison, and then so even in US we were apart for some couple of years, and then when we came back, I came back to Bhubaneswar and he came back to TIFR. That's where we got our jobs.
And there also heard that TFR at that time has some
That was not the only
anti-nepotism
reason. I mean,
policy.
they have, TFR has its own this thing of what it thinks it's higher level and so on. So, I mean, getting jobs in India is not easy. Particularly at that time, there were not that many jobs. There were very few institutes. So I would say that we went where we could get jobs. So I was not prepared. I mean, what was probably at that time unusual is that most women, unfortunately, gave up and went to wherever their husbands got a job. I was not willing to make that compromise, and Ashok was also not, was okay with it, and his family was more importantly okay with it. They said you should do whatever you want, and so we chose to stay in two different places. We went where we got positions.
You mostly at the east side of India and
Exactly.
he mostly at the
I went
west
to the
side
east
of
side of
India.
India. His family is from Calcutta. So I was in fact closer to where his family stayed. We would often meet when either both of us would go there, or we would take these long train journeys. It was about 40 hours between Bombay and Bhubaneswar. So that was some, I mean, people used to make fun of Ashok that he always had several tickets for Bhubaneswar in his this thing. So whenever we could, we would take these.
At those time, mobile phones also not
No,
there.
there was no
So
mobile
how
phones.
do
There
you
was no
communicate often?
emails. Email and all came after that.
90s only. So
Yeah, exactly. So we came back in 87. I came back in 87. He came back in 88.
then almost a decade you lived
so
as
we
a
till
single woman.
95. Then Professor Mani, who was also Ashok's teacher at IIT Kanpur, and they started a new institute in Allahabad, Harishchandra Research Institute, where he offered both of us positions. And yeah, it was a brand new institute, so they had a lot of positions available, so they could offer many people, and they offered both of us. And at that time, I think there were in many institutes these anti-nepotism rules that they would not give husband and wife the position in the same place, which they still follow informally in many of the institutes till today. But at that time, he broke that and gave both of us, and that's how we started.
After 10 years of research in elementary particle physics, you chose a shift to condensed matter physics. So, looking back, how do you reflect on that decision?
I think there were many personal and other reasons which I've explained elsewhere, that since Ashok was getting very famous in his field, it was better for me to move slightly away. But also my interests, actually I was working on even much earlier on what is called topological theories. They started gaining importance in this condensed matter physics. Anyons, which I will talk about later, is one of these things, which I had worked on even as a high energy physicist, but that was being applied in condensed matter physics. There's something called the quantum Hall effect, and the kind of particles that I was studying as a very abstract thing in particle physics turned out to be relevant in these.
All these areas are relevant now.
Yeah.
Very relevant.
Exactly. So it became then I got interested in them, and so that seemed like an interesting field to study. It was more concrete. It was less, I mean, there were a lot more problems. I mean, one of the things is that you're looking for interesting problems to solve. And condensed matter is a field where there are a lot of experiments going on always. And there are a lot of interesting problems which come up. In India, one of the problems used to be that not too many experiments, particularly because experiments are expensive. It's harder to do them here. Now there's a lot more money for experiments, so people do these experiments. And when we came back also, what is called the archive, physics archive, had just started, right? So it was not easy to get preprints from abroad. It would take time and all that. So when you start, all these things are difficult. I did not have contacts abroad because my advisor was from high energy, and people I knew were all in particle physics. But slowly you develop all these things.
So it was a struggle at those
times. At that time it was a little bit of a struggle. And then you have to get, the way I would say, helped is that once I started having students, I started having young colleagues with whom I could discuss, and we could all learn together. In many of these things in condensed matter physics, I used to learn along with my students, because for me also some of those things were new. So that was part of the fun of
that also gave the joy of learning
with the
things. This year we celebrating 100 years of quantum mechanics.
Yeah.
And Microsoft announced last month about they invented the topological quantum qubit, Majorana 1.
Yeah.
So this was very much related to your current research topic.
Yes. Because actually anyons, I mean, when I talk about anyons, they are particles which are earlier you normally think of bosons and fermions. And in fact, quantum mechanics, when quantum mechanics started, that's when all this year is also 100 years of Bose.
Before that, there are classified, the particles are classified into two, bosons and fermions.
Yeah.
Bosons are identical.
Bosons,
when they stay together, they are identical.
Identical particles, when you have identical particles.
But their mirror images, for bosons, mirror images are same. Is it like that?
No, I would say that bosons, when you exchange bosons, you get the thing is, Bose and all these people came up, people used to think of particles as distinguishable, that you can distinguish one particle from another particle. 100 years of Bose was also being celebrated. He showed that if you think of them as indistinguishable particles, as all these particles are identical with one another, then there is a kind of thing that you can get some extra, that if you exchange them, whether you get a positive sign or a negative sign under exchange. You take one particle around another, and then the quantum mechanics tells you that you have to describe things in terms of wave functions. Not exactly as where the particle is and what its momentum is, but instead of quantum mechanically, you write down a wave function for them. So for bosons, what happens is if you exchange particles, you get a positive sign. And for fermions, if you exchange two particles, you get a negative sign. For these anyons, you can get anything, any phase. You can get arbitrary, what is called an arbitrary phase.
How can we imagine such a particle which is neither positive nor negative?
It's not charges, it's like something else. I mean, you would say that, it's like you can think of particles are being very much entangled with one another. All of them are being kind of an entangled state.
These bosons and fermions are three-dimensional, but these
anyons can only live in 2 dimensions.
So how can we compress these 3-dimensional particles to 2 dimensions?
It's not that you compress the 3 dimensions. What you think of is that you can actually make single layers of atoms these days. There's something called graphene, which is a single layer of carbon atoms, right? So it's like this is a 2-dimensional, you could call this a 2-dimensional system. Now what you want to think of is what happens, how do you classify particles in these? I mean, there are things which are called excitations, quasi-particle excitations in these particles. Those things can be anyonic. So you can think of them as some kind of particle. It's okay, I will say, how would I think of a quasi-particle? Analogy I will give is bubbles. The bubbles don't have the bubbles are made up of the particles if you have water, bubbles are made up of waters, but bubbles have their own existence. You can have two bubbles which can come together, they can bounce off each other, they can join together, make a bigger bubble, they can disappear, right? So those are what I would call quasi-particles. So what happens is that many times, even in 3 dimensions or in 2 dimensions, you cannot think of the particles, the original particles are just sitting in their positions. But what is moving around in this kind of liquid, or it's often called a Fermi liquid, right, are these bubbles, which are called quasi-particles. And these quasi-particles don't have to be made up of the original particles. So they can be the fermions, they can be bosons, they can be these anyonic quasi-particles. In 2 dimensions in particular, they can be anyonic quasi-particles. And so those are the kinds of particles that I talk about. And for these Majoranas that have recently been discovered, it's even more exciting, because somehow it's like you can think of some kind of an electron, and you have fractionalized the electron and put part of an electron somewhere and part of an electron somewhere else. So it's like together they can form an electron, but they in space they have been
the mass
set
of
apart.
electron
So
is
these
very
quasi-particles, these are not really electrons, these quasi-particles are called Majorana particles.
they are that is, this Majorana particle is actually from electron, but it is quite different from
It's quite different from electron.
and its mass.
You can think of them as quasi-particles. They are what are called a zero energy state. So it's better not to think of them as masses or something like that. You just think of them as some kind of states, and with
A new state of matter.
new states of matter which have these quasi-particle excitations. And why are they important? And then for this Majorana and so on, is because normally electrons, if you another electron, or if it's a spin, it can flip a spin. When you think of normal bits, qubits, even quantum bits, the quantum bits are made from spin. Then if you have some environmental noise, it can flip the spin. Here, because the electron itself has split and put into 2 different parts, it is something, it is not, the environment cannot change it. You have to be able to change things at both the ends of the quasi-particle at the same time. Only then it can flip. If you make some noise at this point, and this is a joint particle, it cannot change. So this is something which is called fault-tolerant quantum computation. So this is the excitement of what is there in this Majorana. People have made qubits before. Normally, normal computers are made of classical bits. Now people are talking about quantum computers which are made of qubits, right? Google and all have come up with these qubits and some quantum computational things of them. This is going one step ahead. It's fault-tolerant quantum computation. I don't know if I'm making, because of the fault tolerance. And the fault tolerance comes from the fact that it's because these are made up of what is called non-local particles. The quasi-particles are at different parts in space. So you can't easily move them or change them. The environment or disturbances or noise cannot affect these particles. So if it really comes up, I mean, this is only 2 weeks old, as you know, the Majorana 1 processor that they talked about. If this comes about, it will actually give a huge leap, a quantum leap, the ability to make quantum computers.
The electron's mass is very negligible when compared to proton or neutron.
Yeah.
And when we split this electron into Majorana particle, what are the conditions required to achieve that?
It's not that you can think, I'm giving a figurative this thing of splitting an electron, because it's not really, you're not taking an electron and splitting. You're taking a system which is made up of electrons, and it has what I'm calling these bubbles or quasi-particles, which behave like as if they're half an electron. Because if they bring them together, they will make an electron or they will disappear. If you bring 2 of these Majorana quasi-particles together, they have 2 possibilities. They can either become an electron or they can completely disappear. So that's, in that sense, I'm calling these Majoranas as half an electron. But it's not that you can think that you're going to split an electron, because
Not
you know that electrons cannot be split. Electrons and quarks, you don't think you can split them, right? They're considered elementary particles.
Think it as a constructive way, that is.
You're constructing these Majorana quasi-particles at the ends of a semiconductor wire, and that's the kind of architecture this Majorana.
Oh, then what is this topology?
Why is it called a topological qubit?
Yeah.
I'll have to explain some other things to say what is topology, right? Topology actually comes from the fact that you can have knots in the system, piece of wire or something I can demonstrate, or you can think of something which is a solid sphere and something which is like a donut, a vada, with a hole in the middle. Those things you cannot, a sphere can be moved into it by like plasticine or something. You can make it into many shapes. A sphere can be made
Sphere
into
can
a
be moved into a
disc or something like that. But you cannot make it into a torus, a hole in the middle. I mean, you have different topological quantum numbers which will give each of these things. Now, similarly, in these Majoranas and so on, what you have are quantum numbers in what is called the momentum space, which distinguishes whether something is a trivial, I mean, whether it's analogous to a sphere or whether it's analogous to a cup or whether it's analogous to something else. In that sense, topology comes into this. But to explain that, one has to go into a little bit more of technicalities of what you want to do.
Can you say how far we are from a practical quantum computer now?
Yeah, that's the million-dollar question, so to speak. People have made quantum computers and they are making the which are larger and larger. I forget now, it's 50, 56, 50 or 100 something qubit machines that people have made. I think Google has made one of these quantum computers, and what they have shown that you can do some kinds of artificial problems on this which cannot be done by a classical computer. So in that sense, they have shown what is called quantum supremacy, that there is something that this quantum computer can do which cannot be done by a classical computer. But the thing is, right now what they've shown is an uninteresting problem. For any interesting, nice problem, as of now, classical computers have done better than quantum computers. Now, with this 2-week-old technology, if it is true, if it is proved, what they are saying that what people earlier thought would take decades to do, they claim that in a few more years they will be able to achieve a huge, because in this bit that they have in this topology, the processor that they have made,
This Majorana
processor, right? Right now they have, I think, eight topological qubits on it. They think they can put 100,000 topological qubits on it within a few years. But this is a claim. So I
not
don't.
yet proved.
It's not proved. And even the technology of this, the existence of these Majoranas have, again, Microsoft has done the only experiment which shows that there exist these Majoranas, and even that no other group has replicated it, and I would say in that sense it is still not proven. So how long it will take to get a practical, okay, it was nice that they made something that you can hold in your hand, but whether it's going to be, how long it will take, I don't know, 10 years, 15 years, 20 years. I'm hoping it will happen.
And how long it will take to get a computer, a quantum computer, as like a desktop computer or a laptop
Again,
size?
I mean, yeah, if you believe these people, maybe 20 years, 10, 20 years, you should have it. I would believe it, so it will happen, because things always move faster than
expected.
Yeah, in some sense, yeah. Okay, I'm an optimist, let's say it that way.
Will this approach will surpass other quantum computing models?
If it is true, I think it, I mean, as compared to more the non-fault tolerant, the usual non-topological qubits versus these qubits, I believe it will.
There is another curious question, that is, throughout history, civilizations have been defined by materials. The Stone Age, the Bronze Age, Iron Age, Steel Age, then the Silicon Age. So given our progress in nanotechnology, nanomaterials and quantum technology, what age do you think we are currently in? And what would be the next
maybe
stage?
I would call it still the graphene age. There's a lot of
It's the
things.
graphene age now.
Yeah, so I think new and newer material, graphene and 2D material age maybe.
Graphene is 2D.
Graphene is a 2D material. There are other kinds of 2D materials.
So this is 2D
maybe a lot of
material
these,
age.
like semiconductors and all, maybe transistors, many things can be made from graphene. But going forward, I would say topological age, artificial intelligence age, right? There are many, I don't know what exactly will be the defining this thing.
So what would be the stage that is this combining this AI technology and quantum computation techniques?
Yeah, so that will be the new,
How you foresee
going
that
forward, I
age?
would think that maybe machine age, artificial intelligence age, that humans will be competing with artificial intelligence and maybe they will take over right? So that would be what I would.
And your work spans multiple fields, quantum computation to mesoscopic physics. And we could discuss one contribution only. So what would you choose because of the time limit?
Yeah, I would like to say that where I think my contribution I would like it to be thought of is more that in training the next gen, it doesn't matter which of these fields it is. I've had
quantum wires, quantum dots.
Any of these fields are this thing. Most
all are
recently, I've been
relevant now.
working on anyons and topological quantum computation. But I feel that my most important contribution has been in the realm of training. I've had several excellent PhD students, excellent visiting students, undergraduate students, and lot of the work that I have done at any given time has always been in collaboration with my students, many of whom are now faculty members in many different institutes in the country. And I think, so now I have grant students, I work with them as well, my students. So I really think of it as some kind of, the main thing for me which has given me excitement in physics for all these years is my interaction with these younger people, younger students who keep me enthusiastic, motivated. Often this thing is that they see something and say, oh, this is so exciting, let's work on it. So that's, I think, that's why one reason I keep changing my field also, because I get interested in whatever new comes up via the students. And I think in the next few years also, I assume, quantum computation has also been like that. Somebody comes and tells me, okay, this is very exciting, so let's work on this. I would say, rather than pick any of these things, I would say that my general feeling is that I like working on whatever comes up new, like working with students very much.
You have been actively working on the challenges faced by women in academia, especially women in physics. What are your key observations and what solutions you put forward?
Yeah. I think the key observations, of course, most of us know there are a lot of problems for women. There are inbuilt bias, there's lack of confidence sometimes the women themselves, and then there's this two-body problem which I faced and many other women even now are facing, because it's difficult to get two jobs in the same city. And in India in particular, there's a lot more pressure of women getting married, then having children, and then having elderly relatives to look after. And this workload unfairly falls on the women, because very few, this should be equally shared by men and women, right? Either child care, elderly care, all
The
these
household
things.
Responsibility should be equally
Shared by men and women. It should not be burdened by one. And that, as long as that remains, there's a social problem that India has. At the academic institutes level and so on, I think people in the older generation in particular have not realized that they have biases, right? That they automatically think of men as superior. Those things, it's not their fault. They've been brought up in that way. They did it automatically.
It was normal then.
It was normal then. Now the younger people, I think, are improving. From my perspective, when I talk to younger women, they say, no, things are still the same. It's still as bad as ever. But I feel things are improving. The younger people are more aware of their biases, and there is now at the governmental level and at institutional level, there is a lot more this thing. Firstly, even direct things like sexual harassment was not we were, at the first time when we wrote some of these articles, people said, don't mention it. It will hurt people. Now those things are openly discussed. There in every institute you have this workplace harassment, sexual harassment and gender biased harassment to avoid those things, right? All these legally you have to have in every institute one of these committees which will look into these.
Also, there is very few women in the higher levels of the hierarchy here.
There is very
and
few.
Professor Annapurni Subramaniam, in
Yeah.
one of the episodes of the Science Talk, she shared the view that usually there is a bias that, you are a woman, do you have that commanding capacity?
Exactly, yeah. At the leadership positions, at directorial positions.
That is
Yeah.
defined by men's qualities, defined by
Exactly,
men
yeah.
according to men's
qualities. So there is a lot more women do very well, I mean could do very well even at administratively high positions. They're just not even, they're overlooked. In fact, they're not even nominated for these positions. They're not even looked at as possible candidates for these positions.
So far, we have only one woman as the director of a
There's
major.
there's
Professor
SN Bose has a director, Tanushri Das Gupta, she is also a woman, and a few other women there have been now, vice chancellors, all these things. There are so few women at that level, even though they could, many of them would do pretty well, I would think, as women. The other thing I wanted to say specifically is that there are younger women who are very smart and very outspoken, right? They're often thought of as difficult, and then they're not. I mean, I know young women who find it difficult to get positions as faculty members once they're kind of labeled as difficult. Whereas there are a lot of guys also who are difficult, but they get less labeled. Right? I mean, the men also do the same. I mean, sometimes there are people who fight a lot and so on, right? I mean, so, but there are men also who do that, but somehow they don't get as isolated as the women who have these problems, right? So who sometimes get isolated and they're not taken into part of things. So I feel that those kinds of biases against women still remain, and until both the social problems that women themselves, that the family responsibilities get equally divided, and the fact that the two body problems, that there has to be some way of solving it. One of my suggestions, I don't know where to make this, maybe I'll make it here, is that if institutes don't want to hire, say that they cannot hire two people at the same time, maybe you give them an extra position at that time. Don't count it as a, I mean, if they have 25 positions, make it 26 positions if they're going to hire a couple. I think hiring couples should be a priority for institutes. First, it keeps people happy, it keeps them in one place, and it is not that having kids and having a family is the responsibility of women alone. The entire country needs it, right? So you might as well make it easy for people to have careers and couple and family together. You can't expect most people to say that, no, I'll sacrifice one for the other.
And the government should also give paternity leave like maternity
Government should
leave.
definitely, I think there is, no?
In some institutes only.
Yeah, I thought there is paternity leave, they don't take it. That's a different question, right? People should also take the paternity leave.
Due to the time limit, let me stop here. But next time, please give us an interview on the story of quantum mechanics and more detailed story about your research on quantum wires and quantum dots. Also, we would like to express our sincere thanks and admiration for coming to our studio, our respect to your dedication for your students and the teaching community here. Thank you very much, ma'am.
Thanks for having me here. And next time I'll try to explain anyons in perhaps a simpler way than I did this time.